Hello. So we're back with load flow analysis. So as you may have noticed, we're done with Gauss-Seidel and Newton-Raphson, and the end product of those two methods are basically the voltages at the bases. So from Newton-Raphson and Gauss-Seidel, what we actually did is just to solve for the voltages at the bases. So sir, you told us that tuturuan nyo kaming mag-load flow. So where is the load flow in there kung ang alam lang namin is the voltages at the bases? So the idea is basically once you know the voltages at the bases, then it's easy to find the load flow because you now know the difference of the voltages between the bases. Therefore, you now have an idea of what is the current flow, since you know the potential difference and then you know the admittance of the line. So you're able to get the line flow. Okay, so before going to the solution for the line flows, let's just review our our system. We have this system. This is a 3-bus system with bus 1, a generator on bus 1 and bus 3. Yung bus 1 will be our slack bus, and then on bus 2 we have a PQ load 30 plus J40 MVA, and on bus 3 we also have a PQ load 50 plus J50, but we also have a generator on bus 3. Hence we'll be assuming that bus 3 is PV bus. So we want to maintain a 1.01 voltage on bus 3, and then your generator there is scheduled to inject 30 megawatts, and then you have a load there that is scheduled to draw power of 50 plus J50 MVA. So this is our impedance diagram for that. Again, we for simplicity, I just assume that the generator on bus 3 is an ideal generator, so I don't put any impedance value on the internal impedance value on that. And then you have, I used 100 MVA base, therefore I get a 0.5 plus J0.5 per unit on bus 3 and 0.3 plus J0.4 per unit on bus 2. All of the lines are 0.2 per unit in impedance, 0.1 per unit impedance, J0.1 per unit impedance on internal impedance on the generator at bus 1. And then you have this admittance matrix. And then using Gauss-Seidel and Newton-Raphson, we have 1 angle 0 for bus 1, 0.9627 angle negative 3.13 degrees on bus 2, and 1.01 angle negative 2.69 degrees on bus 3. Those are your bus voltages. Okay, so that's basically the end of the Gauss-Seidel and Newton-Raphson. Now let's go back to the power equations on Gauss-Seidel and well, you'll find these power equations on Gauss-Seidel or Newton-Raphson. Okay, so if you solve for the S injection on bus 1, it's basically this formula. On the bus 2, it's basically this formula for bus 1, this formula for bus 2, and then this formula for bus 3. Okay, so solving for each of them, you have this S injection for bus 1. For bus 2, we actually were able to meet the scheduled value for the injection. It's 0.3 plus J0.4. Take note, this is S conjugate. That's why it's 0.3 plus J0.4. But if you conjugate that S conjugate to get the actual S, so it's 0.3 minus, it's negative 0.3 minus J0.4. Okay, take note, all of these values are S conjugates. Okay, and then you have on bus 3, it's negative 0.2 minus J0.3. So if you conjugate the S conjugate, then it's negative 0.2 plus J0.3. Take note, we again, since this is a PV bus, our schedule is on P and not on Q. Hence we get a 30 going in and a 50 going out, or a net value of 20 going out. So it's this negative 2. But since this is a PV bus, we don't treat this 50 as a schedule. Therefore, you get value that is according to the voltages, it's negative. It's 0.3. Okay, so if you plot all of these S's, take note, not the conjugates but the S on the system using 100 MVA as base, you are actually injecting 50 megawatts and 1014.92 mVAR on bus 1, like this one. You are injecting negative 0.3 and negative 0.4, or drawing 30 megawatts and 40 mVAR on bus 2. And on bus 3, you are injecting negative 0.2 plus J.3, or drawing 20 and negative 29, or drawing 20 megawatts and injecting 29.51 mVAR. Again, the values are S injections and not conjugates. Okay, so that's basically it. These are your power injections. Now if you look at the power flows, at the line flows, this is actually the power flow. You can get the power flow from bus 2 to bus 1 as V1 times V1 minus V2 all over Z12 conjugate. Take note, this is just this formula here. This is basically the voltage difference between 1 and 2 divided by Z, and then you conjugate that's basically I conjugate. So this formula here is actually VI conjugate. So instead of divided by Z, you can multiply it by Y. Take note, I use the small letter Y to denote that this is the Y on the network, not the Y on the admittance matrix. Okay, so it's basically VI conjugate. That is S, not S conjugate. As you can see, I think it's visible here. I erased the conjugate here because, well, at first I was planning to use V conjugate I, but mas mahirap siya eh. So yeah, gawin na lang natin S and then VI conjugate. So using VI conjugate, that this is the formula for the power flow on 1, 2. That is from bus 1 to bus 2. Now we also have the power flow from bus 2 to bus 1. You can also get that. Okay? And then I'll show you the significance of solving for these two later on. But I guess the difference is just from 1 to 2, you're actually using the voltage at 1. And with assuming that 1 is higher than 2. And from 2 to 1, you're actually using the voltage of 2, assuming that voltage of 2 is higher than voltage of 1. Okay? So that's basically the difference. And then you follow that pattern for S13 and S31, and then for S23 and S32. And then you get these values of line flows. So you have a real component. This is just power flow, real power flow, and this is reactive power flow. So as you can see on S12, you have a positive power flow of 0.26 real power flow, and a positive reactive power flow of 19.37 of 0.1937. Of course, these are all in per unit, so using 100 MVA as base. So this is just 26.22, 28, and 19.37. Now if you look at S13, you have a positive power flow of 23.7 from 1 to 3, but a negative reactive power flow of 4.44. Okay, so that's how you do that. Okay, and then one more example is S31. No, not 31 kasi tapos na tayo sa 13. Sige, later on. This one. 21. On 21, that's basically S from 2 to 1. You have a negative power flow of real power flow of 26.28 and a negative reactive power flow of 17.24. Okay, so let's try drawing those what do you call this? Those P's and Q's on our network. So on P's, from 1 to 2. Okay, dito na lang muna. Okay, so from 1 to 2, you have a positive power flow of 26.28. Therefore, you have 26.3 going from 1 to 2. From 1 to 3, positive power flow of 23.7. So you have 23.7 going from 1 to 3. On 2 to 1, negative power flow of 26.28, or positive power flow of 1 to 2. It's the same. in this direction. On 3 to 1, it's negative power flow of 23.7 or positive power flow that's going to 3. Okay, from 1. And then on 3 to 2, it's positive power flow of 3.7 going to 2 from 3, or negative power on 2 to 3, negative power flow of 3.7 or positive power flow of 3.7 going to 2 from 3. Okay, so that's basically how you plot the powers, the real powers on the network. And then what's interesting here is that if you add 26.3 and 23.7, you'll end up with 50. 26.3 and 3.7, you'll end up with 30. And 23.7 less 3.7, you'll end up with 20. And that's basically the power injections on the network. So I guess that's one way to check if you're in the right if you're doing the right thing. Okay, so on Qs naman, let's talk about Qs. 19.3, this one. So on 1, 2, you have 19.37. I think I should have written this as 19.4. Anyways, that's this one. And then on 1, 2, on 2, 1, that is 17.24, negative 17.24. So it's like positive 17.24 but going to 2 instead of going to 1. So, sir, why is there a difference on 19.3 and 17.24, whereas we don't have a difference of 26.3 and 26.3 on P's? Take note that these are power flows, and this just tells you that you have a power loss from bus 1 going to bus 2. And where does that power loss go? That power loss is due to your line. And your line, take note, on our original network, we assume that your line is only reactive. We don't assume any resistance on that. Therefore, you don't have a power loss due to resistance. You don't have real power loss. That's why you don't have this power loss. But since you have a reactive element here, therefore you have a reactive line loss here. That's why you have this discrepancy here of 19.3 and 17.9. The difference there is basically the power loss on the line. Same for all of these lines. As you can see, you have one line. Well, if you observe the direction of the power flow, the power from the bus is greater than the power to the bus because you have that line loss. Okay, but still you'll end up with correct summations here. 17.24 plus 22.75. This is actually 39.9. And then you have 5.6 here and 23.9. That's 29.5 going in, which is from here negative 29.5 going out. It's basically the same. Okay, and then here you have 19.3 going in that direction, less 4.4. That is actually equal to 14.9. Now, sir, why is there a discrepancy of 1,000 here? Okay. This is 1,014.9. This is 14.9. Why? Where does that 1,000 go? Now take note. I want you to take note that this diagram this is actually from our discussion on admittance matrix. To get the admittance matrix, you don't represent this. You don't represent the network this way, but instead, since you get the admittance matrix through KCL, we use source transform on the generator to represent it this way. Therefore, you actually have this invisible line there that represents the internal impedance of the generator. And if you get the S from 1 to 0 or 1 to ground, that is actually J10 per unit. If you use this formula, instead of 1 to 2, it's basically 1 to 0. So it's V1 times V1 minus V0, which is 0, all over Z10 or 0.1 per unit. 0.1 per unit I. 0.1 I per unit. Okay. And then conjugate. Okay. So that's basically how you get the power here. And that power is actually equal to 10 J10 per unit, or in terms of MVA, it's 0 plus J 1000, because it's 10 times 100. Okay, so it's J times 0 times 1000. Okay, so you have this 1000 here. So now your KCL on powers is now correct. You have 4.4 going in and 1014.9 going in, and that is equated to 19.3 going out and 1000 going out. Okay, so this does not appear on generator 3 on bus 3. Take note, we also have another generator on bus 3, therefore its representation must also be this way. But take note that we assumed that the generator on bus 3 is ideal, so you don't have this one on bus 3. Okay, but if the generator on bus 3 is not ideal, so you'll also need to solve for S30 so that you get the correct power flow. So that's basically power flow. So you solve for the voltages first using Newton-Raphson, Gauss-Seidel. There are actually a whole lot of methods there. You have the DC load flow, and then there are actually a lot of assumptions done on Newton-Raphson to arrive at other solutions. But Newton-Raphson is good enough together with Gauss-Seidel. So that's it for load flow. And then after solving for the voltages, you solve for the line flows, and that's basically load flow analysis.